Welcome to Advent of Code in F star. This is day 17, I believe. We'll get started in just a couple of minutes. So F star is a general purpose functional programming language, as the page says, aimed at program verification, which means you can prove the correctness of your code using dependent types to make statements about what is true or not true about your program. This year I've had limited success actually proving that the solutions are correct, but I've done okay at actually solving the problems, although using F star takes a lot longer to do than other languages I'm used to. So let's put up today's problem. Let's actually tell Twitter that we're starting. Apologies, I usually have that queued up. All right, so we've got finally decode the else message. Hi, it says. Okay. The probe launcher can fire the probe with any integer velocity. Okay. The probe's x position increases by its x velocity, y position increases by its y velocity, the x velocity changes by 1 towards 0, and the probe's y velocity decreases by 1. Okay. For the probe to successfully make it into the trench, this probe must be on some trajectory that causes it to be within target area after any step. Okay. Are we going to have to do some calculus? Okay. How high can you make the probe go while still reaching the target area? Okay, what is the highest? Huh. All right. Well, the good news is we're not going to be doing a lot of string parsing today. All right. So this y is above our starting location. I don't know if that tells us anything. So let me let's see. Feels like we could just do some math on the possible x velocities. That this range since the coordinates are independent, this range by itself gives us a range of starting x velocities. And similarly, this gives a range of starting y velocities. So, if I remembered my high school physics or my college calculus, we could probably do some of this, approximate it. So let's see. What is the x position going to look like? So it's going to look at like, x velocity plus x velocity minus 1 plus x velocity minus 2, etc. And we'll stop when it hits 0. So the sum after n steps equals n times the initial velocity minus the sum from 1 to n, which is n plus 1 times n divided by 2. Right, that's the standard formula. Okay. So that's a mathematical proof. Can we write that as a proof in code? That seems interesting to do. All right, so let x pos n, where n is a natural number terms and init velocity all right. So I'm not going for speed here because I'm so excited there's something here I may actually be able to prove. I think, from this we'd be able to invert it and see, given, I guess that's given where n needs to be. I guess we got 2 degrees of freedom yet. All right. I'm presuming to get as high as possible, though, we would want the initial x velocity to be low, so we spend a lot of time going up and coming back down. So we could have a very high velocity, y velocity, and it would have a lot of turn to get us high up in the air before it started coming down. All right, or in the water, I guess. Okay. So recursively, this is, so if n equals 0, then 0, else it's init velocity, so initial velocity plus, so let me just double check that in the description it's, yeah, we increase the position and then we increase the position and then we slow it. So all right, and I'll make that a integer just to permit us to go backwards. Should we cap it at 0? Maybe. Okay, I didn't close the parenthesis. All right, so our theorem above is that for any I'm gonna make this current velocity to be clear. It's the initial velocity at time 0, but it's the current velocity later. All right, so this is a lemma, and what we want to say is x pos n at time n with init velocity is equal to multiply n and x position and init velocity, which I called xv above, minus n plus 1. We need to multiply again. Multiply n minus 1, n plus 1, n divided by 2. All right, so that's what we asserted. It can't prove it, but we should be able to prove it automatically, but we should be able to prove it by induction. So if n equals 0, then it's 0, no problem. Else, no, all right, that didn't work. Oh, no, all right. I get it right. I think so. All right, so this tells us that x position n minus 1 init velocity plus 1 equals n minus 1 times init velocity plus 1 minus n times n minus 1 divided by 2. What we want to prove is that x pos n Am I doing this the right way? All right, if we were doing a proof by induction, we'd say the base case works. We assume it for all k less than n. That's what we did. I just think I'm maybe doing something wrong with how I'm handling initial velocity. All right. I mean, this should be true. Okay, and what we want to say is, okay, so that is, so we know this is, it's init velocity plus n minus 1 curve velocity. Is there a formula wrong here? Did I screw this up? So this is going to be current velocity plus current velocity minus 1 plus current velocity minus 2 plus, all right, so that's right. Okay. All right, so we definitely need minus 1. Okay. So is this even true? Yeah, so after n, it's going to go for, all right. So this is init velocity plus n minus 1 init velocity minus 1 times n minus 1 minus n times n minus 1 divided by 2. Okay, so this is, all right, so this part is right. And the second part is, I mean, we could just ask it. All right. So is it true that minus n minus 1 minus multiply n minus 1 divided by 2. So to make this work, we need that to equal I didn't think basic algebra would be such a problem, but it's been a long day. All right, it says no. So what is that actually equal to? It's minus n plus 1 no, it's equal to minus n plus 1 times n minus 1. That's not right. Did we drop a 1 somewhere? No. Did we get the formula wrong here? Plus 1 divided by 2 times n. No, that's right. Okay, we did get it wrong. All right, so there's the problem. So it's actually 0 plus 1 plus 2 plus n minus 1. Yeah, after one step, it's 0. All right, there we go. All right, so that is n minus 1 times n over 2. All right, so let's try this again. Minus 1 all right, we get the formula right, we can prove it. So we found my bug. Didn't tell me what my bug was, but it definitely told me I made one. All right. So otherwise it's current velocity plus n minus 1 wait, that's not the same formula. All right, so let's go back and fix. So this is a perfectly good proof for y. But x is going to have to be a little more complicated. So we could have something that just goes up and up and up and it stops and then it turns and falls. So we could make one that might let us get up even higher. All right, so we have to change this. Okay. All right, so if the current velocity is 0, we just stay there. We don't slow down. All right, so now our lemma is false, and we gotta fix it again. So let's do this by requires something. All right, so it's true if init velocity and n is less than the stopping time. So the stopping time is when this quantity equals the initial velocity. So when n minus 1 times n, oops, I use op multiply. Today might be a good day to import that module that makes star the multiplication operator. So this divided by 2 has to be less than or equal to init velocity. And that's not gonna do it. I got it upset with me again. Okay, so what it's actually telling us is we couldn't prove that it couldn't prove that the precondition still held. Okay, so after velocity equals 0, then it's maybe it would be easier to write this as a function. I'll leave that be. If we've just done a brute force search, we might be done by now. All right. So if n minus 1 times n Oh, okay. Oh no, we step by 1 each time, so we won't miss 0. But will this might not match. Okay, that's the problem. That's a problem at least, right? This last term might not be n minus 1. Right? It might be a smaller value that stops us at no. No. All right. So initially it's going to be plus xv minus xv minus 1, which is plus 1. And it's going to be plus 0 forever. Okay. So I was overthinking it, right? When are we at 0 after n steps? So if n is greater than or equal to the initial velocity, then it's okay. Xv times xv minus xv minus 1 times xv divided by 2. Right, that's when we're at 0. Okay. There may be a cleaner way of saying that. Else, it's going to be this version. Phooey. All right, so our lemma is that these are the same. I don't understand the problem here. We checked if n was 0 before. Oh, let's try that. All right, well, let's just make sure I'm not losing my mind here. All right. So what is the problem with proving? Okay, if it's 1, okay, it needs to be greater than or equal to 0. All right, it turned out to be easy once we got the. All right, so it did all the complicated math and checking our cases for us, fortunately. So we've got a closed form. All right, so now what we're going to do is we're going to we're going to use our closed forms to find maybe I didn't think this through enough. All right. What was I thinking before we got tied up in proving their closed forms? What I was thinking is from this closed form, we should be able to tell whether from these two closed forms, we can tell whether or not it's going to be in the bounding box. Okay. Is that the right thing? So as we all right, so we can start with a very high. Oh, it's actually has to drop below. Okay, so given x and y, can we predict what the maximum is? All right, we need to keep the constraint that there is some n in at which it's in the bounding box. Can we go further than that? I mean, it doesn't do us a lot of good to calculate the closed forms if we're just going to iterate one step at a time anyway. So it seems to me that we should be able to reason about these. We should be able to say, all right. So the derivative with respect to n is yv. Doesn't seem right. Oh, yeah. Okay. This is minus n squared minus n divided by 2. So that is so the derivative is 2n plus 1/2. So that when y minus 2n plus 1/2 equals 0. So the high point is either comes at n equals is that true? So the integers on either side of those are the maximum height. So let's try to prove that. Can we do that? Is it? It is symmetric. It's a parabola, isn't it? YV minus derivative of n squared is 2n divided by 2 is n. Yes, I got that backwards. but not 1/4, I think, just 1/2. Yes, thank you. It goes a lot easier to prove things when I prove the right thing. Why am I so much better at algebra when I'm writing it in my notebook? Maybe I should be scrambling on my notebook, but then I can't share it on the screen. I don't have a spare camera. All right. Could be. All right. So n equals minus, n equals yv plus 1/2. Okay, so it could be on either side of that. Still wondering whether I made a mistake. Okay, all right. Well, let's try to prove that. All right. So y pos maximum So our lemma is okay, let's write the closed form as its own function. Oops. Phooey. Yes, that's what we wrote. Actually, calculate from there. So, uh-oh, what did I do? Oh, it just says it timed out. All right. Well, guess that's gonna be a problem for a while. All right. Y closed form. Okay. So what we said is the closed form of y pos y closed form of okay. Okay, let's write this. Okay, so what I was thinking was I would show, oh, it's less than 1 on one side, and it's less than if we decrease by 1, and it's greater than if we go back to 1. But let's say, um, so let's instead say, just say the maximum is at okay, so if we're aimed downwards, then our highest position was in the past. Uh, so, uh, okay, we'll say that this is true is at least 0. Because if the initial velocity is less than 0, then the maximum is at 0 instead. All right. We're working the solver hard today. Yeah, I think we're gonna have to put more work in. All right. All right. Well, how can we convince F star of this fact known to every high school physics student who has seen their teacher fire a banana at a falling monkey? Yes, my high school physics teacher actually did that. Um, yeah, so one thing we can do, since I'm short on ideas right now, is we can actually say, I haven't done this in a while. We can ask it to log its queries. All right, and that creates a file, oops, that is in Z3's scheme-like language. And it's hard to work through. But you know, it's commented with what line of the source is it querying, and you can see the formulas that it says it's encoding before they get into Z3's language. So this is, I think, one of our inductive proofs. Oh no, this is actually a termination proof for our recursive function. I think. This is I think, because this ordering relationship is how it proves termination. So I think this is just the query it sent down to verify that the function actually terminated. And so here's the much more complicated query it sent to verify our lemma. So unfortunately, there's a bunch of stuff in here where it's checking the total effect at the same time as it's checking our formula. But if you sort of squint at this, you can see the inductive hypothesis in the base case here. And so the one that's timing out is this one. So it gave definitions of closed form and Y closed form already. Of Y closed form already. But they were evidently not enough to specify this. So let's say all right, so let's just play the game of what does it know? Does it know that if we decrease n by 1, then the height is lower before that point? Oh, well, okay. All right, so this might hint at a reason why it's not able to prove it. If initial velocity is exactly 0, no, that should be okay. All right, couldn't prove that. I mean, it doesn't do calculus. It only does integer arithmetic. But it seems like this should be something we can prove. Maybe, okay. Hello. I've been mainly doing algebra, and F-star has been checking my algebra. I haven't been doing a very good job of it. Now it's trying to check my calculus. It's very simple calculus. Why am I doing calculus? Because today's Advent of Code problem is all about discrete parabolas. Shooting our torpedo into our probe into target area. And I decided it would be more fun to try to prove as much as we could instead of brute forcing. Okay. So all right, so at it would probably be easier to do a brute force solution and would probably be faster. But since this is something I think I could actually prove, I'm interested in stretching a little bit and trying to prove it. All right, so what that says, the max height equals net velocity times, I'm just going to call this IV. Minus IV squared divided by 2 plus IV over 2. So can we prove that that is the case? All right. So let's actually write that as a function. So okay, screw it. I need a star. Is it mul? Yes. Maybe we better be careful about this. And divide like that. This is definitely causing us problems. And if that is sort of making the solver work hard. All right, so our theory is I did hear about Log4Shell. All right, maybe we'll get lucky. Just knows how to prove it. No. All right. Fortunately, I am not maintaining any Java code, or I probably would not have time to do Advent of Code. I sent out HugOps on a previous day to everybody dealing with patching all their stuff. All right, so if did I at least get the formula right? Uh, doesn't think that I did. Okay. Yeah, we're good. All right. Yeah, when it's can't prove the lemma, it underlines everything, and that's confusing when it's just an assertion. All right, so it knows that this is true. Good. So how do we prove this using discrete mathematics? What we could do is perform induction on how far away we are from all right, let's give this a try. So let's break it into two cases. So when n is all right, when n is less than init velocity, let's say less than or equal to. All right, so if n equals 0, is that a gimme? All right. All right. Since I'm not coming up with anything else, well, this needs to be recursive now. Okay. So it did the math, said sure. So let's try it for everything greater than the or equal to the initial velocity. So if n equals init velocity, oh, this is coming from the plus direction. Yeah, Yep, we're making it work hard, and so it's getting less reliable. Come on, you did it before. Oh, come on. We may need to give it some hints. So it's interesting, the F-star paper on tactics talks about exactly this sort of thing, that Z3 is not deterministic. And so for the very complicated sort of things they wanted to prove about cryptographic primitives and operations in finite fields, it failed quite a lot. And so, introducing a tactic that simplified the goal and could itself be verified made the proof a lot more, made this operation, the thing I'm experiencing right now in this fairly simple case, a lot more reliable. So it went from like solving it 15% of the time at a limit to 100%. All right. So all it took to prove the thing we were trying to prove is to break it into positive and negative parts and give the solver enough time. So maybe if we had given the solver lots more time, it would have been able to do that itself. But this is a fairly common proof technique. It's divided into the two cases and solve each case simultaneously. And it managed to do this. It just takes a lot of CPU time. My fan goes on and worse for a while. All right. So, we can, now that these are proved, I just unproved it by deleting this. We could we can prove it for all n by just saying, well, it's true for those less than or equal to init philosophy and greater than equal to init philosophy, and that's all the natural numbers. So if n is less than or equal to init philosophy, I guess that first one has to be minus. Oops. Oh no, we're going to have to start over. So it's going to have to do a lot of the hard work again. So one of the things, all right, why is it unhappy? Oh, minus. And this doesn't have to be recursive. All right. So it said, hey, that's no problem. I got it. So one of the things we can do that I don't entirely understand is we can output a hints file. So if we do that, maybe some of the replay will be faster. don't know for sure if we can do that with Emacs. Emacs mode. Well, that's type hints. That's not the same thing at all. Ah, there it is. All right, let's put that in my .emacs. I wish I could set it just for this one directory. I guess I could do set options at the top of the file. Let's try that first. Okay, I'll leave this here. Use hints and underscore. Unrecognized option. Oh, underscore. Right, there we go. Well, that sucks. All right, so we gotta do it in the Emacs way. See if that works. All right, ran without hints because it couldn't find the hint file. All right, so what happens if we change that and put it back? It's not feeling a lot faster. That is in fact feeling slower. I don't see a hints file. Nope. It's okay. It's getting passed in. I don't know why it's not. All right, not gonna worry about it right now. Try to get back on track. All right, we know where the maximum is. We proved it. We checked our proof, such it was as it was. So the next thing we want is so what is the largest? I think this is going to come down to brute force anyway, because I'm getting tired. How can we constrain our search to those that hit in the target? So, okay, so can we? All right, so we can use our closed form to say, all right, let me try that algebra. So minus 105 less than or equal to that. That's equal to minus 57. So what does that look like? So for an n, it's just a linear inequality. If we fix n, it's just a linear inequality. But if we fix yv, then it's a quadratic inequality, which there are things we can do with it. but I don't. What I've been missing is a way to efficiently get the satisfying pairs out of this. So what I expect is, there's some irregular shape in the possibility space where, you know, and this is probably the wrong shape, but some set of points like that for a particular value of n, uh, a range of y values will work. And it's probably the opposite. It gets smaller rather than larger, but you know. All right, so let's return feasible XY pairs. Except if we use pairs, then we need we need to get star back and not use this. Well, crud. All right, so what we want is given x min and x max. And y min and y max. These need to be ints. This function is going to return a list of points n, x velocity, and y velocity. Okay, so it's going to return a natural number n, and an xv such that x, all right, that our closed form, x closed form of nxv is less than or equal to x max. All right, I'm going to write a helper in range. Okay, min less than or equal to v and v less than or equal to max. So in range Similarly, a y velocity. All right, so that's a very complicated type. And I'm not at all sure. Oh, there we go. Oh, this has to be a dependent tuple. Ordinary tuples can't have one argument depend on the other, but dependent tuples do. So I'm going to do type feasible, and it's going to take all those as parameters. We're just going to have the one type. I may be getting this type wrong. All right, so this here we can do what we want. Say, all right, so those are all the constraints, and n and all right, so that's just an even bigger type. And what we say is, well, this is going to be, we did want all those in the type. I think. All right, so we want this will return a list of feasible objects for those constraints. All right. Is that at least a valid type that we can have? It is. All right. So what I would like to do is be able to bound our search somehow. So we can actually prove that this is a finite list. Right, because we could start at All right, the biggest n can possibly be. All right, so the largest possible n um, is such that we slow no matter how high. No, I'm not sure that they are. It seems like they ought to be, but my intuition on this is very weak tonight. This is what I should have been spending my time doing. So we can obviously reach it in one time by just firing with enough velocity to put it straight in the middle. Can we, if we have arbitrarily, okay, so the slowest our initial velocity is, it, all right. So it feels like, okay, so this is the maximum distance we can get for given initial velocity. Does that help us? So what that says is for given range of x, we only have to search, for given x, we only have to search up to a given maximum. Okay, and when x is larger than the range, we go outside the target in one area. So let's write that down. Okay, so the maximum initial velocity, the initial velocity has to be less than x max, otherwise we overshoot on n equals 1, on time 1. Okay, and for a given xv, we can only no, it's not, okay. When our velocity goes to 0 and we're dropping straight down, we could, in theory, drop down arbitrarily long. All right, can we... All right, so y velocity, can we apply the same reasoning to y velocity? So the y velocity has to be less than y max. Except we're being pulled downwards. All right. What we can say is when x velocity is 0, then y of t has got to be greater than y min, otherwise we've missed. All right, we might still be going up, we might be dropping, but either way we got to be above the max. Yeah. So we're max is minus 57. We better be above minus 57 if we're going to hit it. If we're already no, it better be it was right, I was right the first time. If we're already okay. I think yeah, if we're already below y min, we can't be going back up because we had started at 0. So if our parabola has to be going closed at the top, open at the bottom. All right. I mean, we could just shoot straight downwards, but all right. So that gives us, so we can pick in x from the maximum number of ranges, given that we can find when y is 0 and say, have we missed? But does that still leave, I think that still doesn't bound it enough to do a finite search. And that's what we need to get to, is we need to search only finitely many values of the parameters. So I'm missing something that'll let us narrow it down and narrow all three down. Okay, so what else do we know? Okay, so the more basic way to look at it is, you know, x of t has got to be less than x max, less than or equal to x max, and y of t all right, once we go over, we're not coming back. So we only need to look at values that give us this range, and we could show how are we going to prove to f star that our search terminates? Because if we can prove that f star that it terminates, then we'll only have searched finitely many values. What I was thinking is that we could prove that we're getting closer to these constraints, but I don't actually have a good idea how to do that. All right, I guess what we said here is yt has got to be greater than y min at all points, else we've missed it. And I'm making, if it ever goes below the minimum, we can't crawl back up. And that's assumption that's got a lot of assumptions built in. Because y min is less than 0. So can we actually... What order can we enumerate these in? That'll let us prove that that's the case, that we're making progress. The reason I think the space isn't disconnected might be disconnected is that, if you look at this picture, we might be falling fast enough that for some values we drop over it, and for some values close but not immediately next to it, we drop right in the middle. I think that's feasible. All right. So what we need to convince F star that the search terminates is a metric that obeys a well ordering. So we have to provide a less than relationship where every tuple we search is less than the one before, and we get to define what less than means. But it has to be something it can verify. I think I'm going to have to sleep on this. I need to get up early for flight tomorrow. So I'm disappointed that I could not get further, but I'm just having a hard time reasoning about this. if we could just do the easy thing and uh, search all tuples in sort of increasing order and filter to those that are feasible and just print out the highest height we'd seen so far. And if we let that run a while, we could be confident it wasn't coming up with any answers. Okay, so the adjustment we could make to that is prove that um, we did do some F-star calculus. So the adjustment I want to make to that is sort of prove that there are only finitely many points in that space we have to search through. So if we could do that, then we could use that as a metric. We say, hey, we've searched, there are only a billion points that are possible. We've searched 1, 2, 3, 4, 5, 6, 7, 8, 9 of them, and so the number's going down. But I'm not so I've only found one bound on that size, and I'm not coming up with how we do the rest of it. So I'm gonna, like I said, I'm gonna sleep on it. Thanks for sticking up with me, and I will. Tomorrow's gonna be a long day, but I hope to be able to do live stream. I'll be back on Central Time, and so it'll be easy to start at 11 o'clock Central. Good night. Happy Advent.